So yes, welcome to the Master Electricians at IPD technical webinar on RCD Essentials and the effects of the changes to the standard. This is covering off the changes implemented with the Amendment 2 to AS 3000 2018 edition that had a 24-month delayed transition period. Joining us today, we have Ian and Fred, both from IPD. They're going to give us a quick little introduction of their roles with IPD, and they'll be taking over the presentation today. But I'll be here to moderate. And as I said, any questions you have throughout, please check for the Q&A box at the bottom of your screens. Enter your questions in, and we'll read them through. And there will be a large Q&A session panel at the end of today's presentation. All right, take it away, Ian.
Okay, thank you very much, Matt. So as Matt said, I'm Ian Richardson. Fred, my colleague from IPD, is also joining us, and we've both worked in the industry for probably too many years than we care to remember, and we've delved into the area of residual current devices for quite some time. So let's hope you find the information that we've got informative. So first of all, thank you very much to Master Electricians for hosting this event. We'll start off with the introduction, which we're doing right now, and then we'll lead into why do we actually need RCDs and what is an RCD. We'll then jump into a bit of old tech school work. How does an RCD work? And a little bit of information on the RCD tripping times and the threshold currents according to the standards.
Also, why 30 milliamp and 300 millisecond has been chosen for protection of the people, and also what's the difference between voltage independent and voltage dependent RCDs and different type of RCDs, and what changes in the industry standard and is happening, and what does it mean for you?
That's a good intro there, Fred. So Fred, we'll start off with a really basic question. Why do we need RCDs?
Actually, that's an interesting question, and good to know why do we use them in Australia. In the 1990s, there was an average of 49 electrical fatalities per year recorded in Australia and New Zealand.
You know, in the year 2000, there was a new edition of the Australian wiring rules, AS 3000, that came into effect. And this increased the requirement for residual current protection in all installations.
Yeah, and in the decade following 2000, the average fell to 28 electrical fatalities per year.
That's impressive. And, you know, since the year 2000, the electrical fatalities have actually continued to trend lower year on year. If we look at the year 2000 to 2001, there was 1.7 deaths per million people. That's an interesting benchmark. In the year 2019 to 2020, that had dropped to 0.34 deaths per million. And last reported year was 2021 to 2022. That went down to 0.29 deaths per million people. Unfortunately, since the year 2000, there have been over 350 fatalities in Australia. But the trend that we see shows that the introduction of RCDs has had a significant impact on the safety of consumers.
Okay, and so what is an RCD then?
RCD, yes, it stands for a residual current device, and it's a protection device against earth faults. We have to remember, though, that an RCD cannot prevent an electric shock. It is used to prevent the risk of death for humans and the risk of fire and damage in buildings and equipment. There's been a lot of research over the years, and this has shown that nearly 90% of electric shocks are from an active conductor down to earth. And this is exactly what an RCD can protect against.
Yeah, and RCDs can come in several forms. A residual current circuit breaker, or RCCB, is an RCD with its own poles for isolating the supply, sometimes generically called RCD, especially in domestic applications. They can also be called safety switches in domestic application as well.
And we also have an RCBO. And I'm often asked, what does an RCBO actually stand for? It's technical name is the residual current circuit breaker with overcurrent protection. And this is effectively a residual current device that also incorporates the thermal and magnetic protection for the main poles. This can be called a combined MCB-RCD, or in the industry, we often call it a combo, just for short.
Yeah, and also we have an add-on RCD or RCD block, which is an RCD similar to our CCB, which can be attached to a miniature circuit breaker to form an RCBO. This allows the use of more specific MCB combinations, such as D-curve MCBs.
That's really handy. And the final one is an RCD relay. And this is a form of RCD that doesn't have the isolating contacts for the main power circuit, but it has a relay output. And this would normally drive a shunt trip to open a relevant circuit breaker. The RCD relay will often have a separate external toroid, which can allow a variety of cable sizes for the power cables to be protected. And that can be quite convenient in some installations. RCD relays have an adjustable sensitivity and adjustable time delay functions. But we've got to be careful. The wiring rules tell us that we have to use a fixed setting RCD, not exceeding 30 milliamp, when we're talking about people protections. So this really means that we cannot use an RCD relay for final sub-circuit residual current protection.
Great. So now that we know what this RCD is standing for, how does an RCD work, Ian?
It's pretty simple, really, Fred. The current flowing to the load, runs through the RCD main poles, as you can see on this diagram. And this creates a magnetic field which generates a current in the toroid that the main pole is passing through. The circuit is completed when the current returns from the load and flows through the other pole. So both of those pole currents will flow through that toroid. This creates an opposing magnetic field, which also generates an opposite current in the secondary, the toroid. So if there is no earth fault, these two magnetic fields and the currents will cancel each other out, and the net result obviously is zero. The same cancelling effect occurs if it is a single phase or a three-phase device. The RCD will trip on the imbalance between the current flowing to and from the load, not an imbalance between the phases. So this device is fine if there's an unbalanced load.
Yeah, and the RCD test button creates a real fault by placing a resistance across the toroid and tests every part of the function of the RCD. So Ian, what do the standards say about the sensitivity of RCDs for people protection?
Very good question, Fred. The standards tell us a 30 milliamp device must not trip at 15 milliamps or 50% of its sensitivity, if we're talking about a 30 milliamp. But it must trip at 30 milliamps or 100% of its sensitivity. And this is typical of the way a standard could be written. Most manufacturers aim for around about the middle of this range, and the actual tripping is approximately 22 milliamps, 22 to 25 milliamps. A 30 milliamp device, when tested at 30 milliamps, is allowed by the standard to take up to 300 milliseconds to trip. You know, it's a common misconception in the market that this value is 30 milliseconds or 40 milliseconds. It's not actually correct. The standard also defines the sensitivity and time of operation for RCDs. The requirement is a tripping time, and it goes like on a sliding scale. A tripping time of 300 milliseconds at 100% sensitivity, as I just said, 150 milliseconds at 200%, and 40 milliseconds at 5 times the sensitivity, or 40 milliseconds thereafter.
Also, there is an exception, which is it's a 10 milliamp device known as type 1 RCD, which must trip within 40 milliseconds regardless of the test current. The trip values are given in table 2, clause 5.3.8 of AS/NZS 61009.1, and you can check it there if you want more information about them as well.
A lot of what we know about the effects of current on the human body is thanks to the work of an Austrian physicist, Dr. Gottfried Begelmeier. He conducted many of his experiments on the threshold of electric currents on the body, and he did this experiments on himself, not that I would be lining up for that job. His work paid off, and he is accredited with the first patent of an RCCB way back in 1957. The international Australian standards show this time current curve that you can see on this slide that defines the reactions on the human heart. In the lower regions, known as the AC1 and AC2, there is a limited reaction of muscular contraction. When we move to the AC3 region of the time current curve, we can experience strong muscular contractions and reversible disturbances to normal heart rhythm. Above the AC4 region, it gets very serious, and there is a really serious potential for cardiac arrest. With all of this knowledge, we can now draw a line between the AC4 curve and the threat of cardiac arrest. And lo and behold, we can see this is exactly at 30 milliamps.
So based on what you mentioned, it's critical to keep it below the AC4 level, which affects heart function. And that is why 30 milliamp has been chosen as the value for people protection as per this red line on the graph.
It all starts to make sense, doesn't it, Fred?
Yeah.
You know, Fred, in the technology of RCDs, we have two styles, the voltage independent and the voltage dependent. A voltage-independent RCDs is sometimes known as an electromechanical RCD, and it uses the energy taken from the core balance toroid to power the tripping circuit of the RCD. The tripping relay used in these products is really highly sensitive, a low-power relay specifically designed and manufactured for this particular purpose.
And the other type, the voltage-dependent style, which can also be called an electronic RCD, uses power from the main circuit to operate the tripping operation of the RCD. This means the RCD needs a power supply in order to sense an imbalance.
That's very true. This table that you can see highlights the differences between the voltage independent and the voltage dependent types of relay. We can see that often the voltage dependent RCD has an additional connection called a functional earth.
Yeah, so the functional earth connection provides an additional safety level for voltage-dependent RCDs. It provides a second voltage reference in case of neutral wire failure. If we have a situation where the following has occurred, the functional earth is not connected, or we have a broken neutral, or it's been disconnected, the active is connected and live, the primary means of protection such as insulation fails, this additional protection, this additional layer of safety with the functional earth will come in. Now, if a person comes into contact with the unprotected active, then that person could be electrocuted.
That's very true, Fred. But remember, this is a functional earth. It's not a protective earth. And that's why it doesn't need to be green and yellow. The standards are clear. A protective earth must be green-yellow conductors, and we're all very familiar with that. It's spelled out very clearly in AS3000. However, the standard's also clear that a functional earth that is provided to ensure the correct operation of electrical equipment does not need to comply with the requirements of the main and protective earthing conductors. You know, Fred, I've even had some people tell me that they cut off the functional earth conductor, and it's really a misunderstanding of why it's there. But as Fred has explained, the functional earth is there as an additional safety for some voltage-dependent RCBAs. So guys, please use it. Don't snip it off. It's there for a very, very valid reason in case that the neutral gets damaged.
Great information. So Ian, we have a number of types of RCDs available. Can you please run through the differences?
Sure thing, Fred. There's quite a number of them, and they all have different characteristics. When we're looking at this table, we have to remember that most importantly, we're talking about the wave shape of the earth fault. We're not talking about the supply mains to the RCD. And people can get hung up on that a little bit as we get into the higher spec devices, which we'll talk about in a moment. The type AC is the most basic version of an RCD which is available. And this is able to detect a residual fault with a standard sinusoidal waveform. With the introduction of electronics, we saw a lot of non-sinusoidal waveforms appear, and the type AC couldn't necessarily detect that. So we needed a more advanced device called a type A. The type A is capable of detecting faults with rectified or pulsating half waves, as well as direct currents superimposed on the sine wave up to 6 milliamps. We're seeing a lot of single-phase inverter technology, such as air conditioners and some washing machines. And this has introduced a high-frequency element to potential earth faults. To detect this, a new, relatively new product called a type F was developed, which also does everything a type A can do, but it can also detect earth faults with frequencies up to 1000 hertz. Where we have loads that provide a full DC rectification, things like a variable speed drive or an EV charger, which are becoming quite popular, a pure DC residual current fault, as well as a high frequency fault, can be seen. So an additional model called a type B was developed. And this is capable of detecting pure DC faults, as well as frequencies up to 2 kilohertz. Sometimes we call that the universal type. The type AC and the type A RCDs have a resistance to impulses or leakage currents and surges up to 250 amps. But due to the more advanced loads they're designed for, the type F and type B have a higher resistance to impulses. And this is up to 3000 amps. So this provides a really good resistance against nuisance tripping.
Yeah, also the type that you mentioned here, this in this table, this matches the RCD types described in Wiring Rules AS NZS 3000 as well.
Absolutely. And Fred, I'm glad you brought up the wiring rules. The Wiring Rules Committee and the safety regulators, they've noted that there's been a shift in the appliances and loads that can generate different earth fault wave shapes. So on the 30th of April 2021, Amendment number 2 of the Wiring Rules was released. That amendment, as we know, included a clause relating to type AC and type A RCDs. So the clause 2.6.2.2.2 states that RCDs shall be of a type for which tripping is ensured for residual sinusoidal alternating currents or residual sinusoidal alternating currents and residual pulsating direct current. So from what we spoke about on the earlier slide, we can see that a type AC complies with the first part of that requirement, but not the second part. The release of Amendment 2 on the 30th of April 2021 saw most of the state electrical authorities like Energy Safe Victoria, the Electrical Safety Office in Queensland and Fair Trading publish on their websites that the overall amendment takes effect as of the 1st of November 2021. This is typical of an amendment. They give a 6-month transition. But there's an exception. To be absolutely clear, the amendment states that in relation to type AC RCDs, for 24 months from the date of publication of the amendment, items compliant with Part A and Part B, as we spoke about, can be used. Following that time, type AC RCDs shall not be installed. And you'd all be familiar, WorkSafe Queensland recently published a notification on their website regarding the use of type AC RCDs up to the 30th of April. So that information is getting out there.
So this means from the 1st of May 2023, type AC devices should not be installed in any projects.
That's exactly right, Fred. We can look at some other styles of RCD as well. In the ABB range, we have high immunity models called an APR. These are actually a variation of a type A RCD with additional characteristics to prevent tripping on short-term transients and surges. In this graph, you can see the typical trip curve of an instantaneous RCD. It's that green dotted line towards the bottom there. The standard requires 30 milliamp RCDs to be an instantaneous operation. However, this is defined by the trip current versus time that we discussed earlier, 30 milliseconds at 30 milliamps, 150 milliseconds at 60 milliamps, and so on. The APR high immunity model still trips under the definition of an instantaneous device. However, they're designed to trip much closer to the upper curve, which provides greater resistance to short-term transients. The APR model can also resist impulses up to 3000 amps, which is just like the type F and the type B.
Yeah, and the other type available is type S. Type S or selective RCD is also based on the type A RCD, but with an intentional time delay built in. As you can see on the graph, the time current characteristic is completely different. We use this in a similar way to discrimination of circuit breakers, which allows us to place an RCD above another RCD in a network. The selective RCDs are rated 100 milliamp or 300 milliamp, and as they have a non-instantaneous operation, they cannot be used for final sub-circuit protection or 30 milliamp. The selective RCDs are sometimes used for additional protection against the risk of fire caused by a current leakage across insulation. So, Ian, we sometimes hear of 10 milliamp RCBO being required in hospitals. Why is it necessary for 10 milliamp?
Fred, a hospital is one of the only places where humans are deliberately connected to electrical equipment. There can be openings in the skin during operations that will reduce the electrical impedance of the human body. There's also a high occurrence of people in a weakened physical state, and this makes them more susceptible to being hurt as a result of a shock.
Yeah, there are some other areas where we may need to use 10 milliamp RCDs as well. In the 2007 wiring rules, it says that 10 milliamp may be considered for areas of higher risk, such as kindergartens or bathrooms. It's recommended, but it's not mandatory. In section 7 of the current 2018 edition of the wiring rules, electromedical treatment areas need to comply with AS/NZS 3003 electrical installations patient areas, where 10 milliamp RCD requirements are mentioned as well.
So there is that specific standard now for hospital environments. So it's worthwhile noting, guys. You know, unwanted tripping is quite a topic, and it's also often called nuisance tripping, and I really don't like this term, nuisance tripping. RCDs are a very, very sensitive device by their nature, and this is because they're a safety device. Usually they'll trip due to an event that has been detected, and it's interpreted by the device as being an earth fault. This means any trip of an RCD needs to be investigated. Often the cause of the trip can be due to the accumulated leakage of a number of loads on the circuit.
Yeah, many electronic appliances utilize switch mode power supplies that can exhibit a small leakage due to the capacitors connected to earth in their filtering circuits. The actual leakage can vary between individual products and manufacturers, so it's worth to have a look at the tables provided by manufacturer, which this table that we have here can provide guidance of the type of leakage that can be seen on various type of equipment.
You know, Fred, I find this table really interesting. Over the years, I've had many contractors say that the RCD is tripping for no apparent reason. They tell me they've tightened the load, it's a 16 amp RCBO, they're only pulling 5 or 6 amps, and this rotten RCBO trips. Often when we investigate the type of load involved, it becomes clear that there could be an accumulated leakage problem. If you consider a typical office environment, you've got 10 computers on a final subcircuit. Perhaps that's not unusual. This is potentially a 20 milliamp leakage, which is available because we know that computers, because of their switch mode power supplies, could have a leakage between 1 and 2 milliamps. So taking the upper limit, 10 computers, 2 milliamps, we're now at 20 milliamps. We're into that threshold where a normal 30 milliamp RCBO can trip. Now, if we start adding on a few monitors and some desktop printers, and they've all got the similar sort of an issue as far as leakage goes, and we can see it starts to make sense that this accumulation of leakages across those loads is the reason that the RCD could trip. I think the table helps to understand the hidden nature of leakages in standard equipment and point us to identifying possible reasons for the so-called nuisance tripping. And just to bring it into context, so a few years ago, when I was working at ABB, we had a high-end fashion store that was being fitted out. It's a Zara store in the Chadstone Shopping Centre in Melbourne. And it was interesting because the Zara stores are all identical across the country. They use a standard design, they use standard equipment. Everything is 100% the same. And in this particular store in Chadstone, they were having tripping of RCBOs on the lighting circuits. So naturally, we were called in as the product supplier to come in and investigate. And once we started looking at it, we said, no, this just smells of accumulated leakage. And the consultant was there saying to us, no, can't be, because all the stores are the same. This is the only one where we have the problem. So we did some further investigation. Well, as it turned out, long story short, on this particular store, they had changed the brand of LED driver they were using. And it turned out that that driver had a higher leakage than the previous ones they were using, probably because they used a cheaper one. And it all just makes sense. So guys, when you're finding that you've got an issue with a tripping RCBO, number one, check the circuit, find out why it has tripped. Sometimes it's very, very hidden and it can be due to an accumulated leakage. So always look to the load to see if you can determine where the leakage is coming from. It's a challenge. I have to admit, it's a major challenge because a lot of the manufacturers of equipment do not tell you in their tech data what the leakage is. They claim that they comply with a certain standard, but they won't actually tell you. So the table that you can see, it gives you a little bit of guidance of what it can be. It doesn't necessarily, it's not cut and dry. You'll get some products in these categories which are better. You get some which are worse. It'll vary a lot. But what our message to you is, if you're having issues, have a look at this, because it could well be the issue that you've got. So with that, I'll hand it back to Matt for any questions that have come through. And just briefly, I'd like to say on behalf of IPD, we'd like to thank MEA for hosting this event, and we certainly welcome any questions.
Thanks, Ian. Thanks, Fred. That was really informative. Yes, guys, so if you do have some questions, please jump on the Q&A box we have down the bottom of the screen and type your questions and send them in, and we'll try to get through to them. As a quick reminder, this session is going to be available to watch later on. It'll be saved, the recording, and every attendee or anyone who signed up for it will receive an email link in the following couple of days once we've had a chance to edit it, and you'll be able to download and watch that yourselves. Probably the first question I had, just came in towards the end there, from Damien, was, is there anything in the pipeline to give a similar protection for phase-to-phase or phase-to-neutral faults? I believe the AFDDs are our new product in that space. Is that something you guys have available as well?
Yes, we do.
Yes.
Fred, do you want to take that?
Yeah, sure. Yeah, we have AFDDs available up to 20 amp, and they come in 2 different versions. And yeah, this is something that at the moment it is not mandatory, it's optional, but there are conversations about it that it might become mandatory soon, but at the moment it's optional. And yeah, we have those products available in our range, which is ABB product.
The AFDDs are a fantastic product, And this is one of the difficulties we have with our traditional methods of circuit protection with a circuit breaker. It can certainly sense a thermal current. It can sense the magnetics of a short circuit. When we're talking about an arc, that tends to be a very low level. And this is where the uniqueness of the AFDD comes in. It can actually detect a waveform, which is the characteristic of an arc. And I think they're a wonderful piece of equipment.
Wonderful. Next question is from Adan. Based on your experience, what would be the maximum number of GPOs you'd recommend on a 30 milliamp RCD?
That is a really tricky question. For any contractor, if you're doing an office fit out, the hard part is you don't quite know what loads are going to be plugged in. So from an accumulated leakage point of view, it is just really, really difficult. I remember when I started out in the trade, we had a defined number of GPOs that were allowed on a particular circuit. And I go way back to the old yellow book of the AS3000. These days, we work on maximum demands and working with circuit breakers. Circuit breaker protection is meant to be the godsend of everything. So, and really a circuit breaker is protecting the cable, not so much the amount of outlets that you've got. So it's hard to give a definitive answer to that, because if you plug a whole lot of devices in there, which have got a known leakage, you will have a less amount. But if you put a bunch of resistive loads in there, for example, which don't really have much leakage at all, you could have a very high number. So I'm sorry, it's really hard to give a definitive answer.
That is a
And
difficult one.
also just to add to one more point is there are two factors at least need to be considered. Is what type of load, in a sense that if you want if you want to feed a kitchen, then you have a microwave, you have a kettle, that each one of them gonna drain something around 10 amps. So your 20 amp are already at the limit of overload. And also if it's like a computer office area, then it's not a matter of the overload, it's a matter of leakage. So it depends on what type of load you're feeding with that circuit as well.
Exactly.
Excellent. The next one here is from Colin. With regards to car chargers, what RCVO should be installed? Consider that some chargers have their own built-in leakage devices. Is the Type A suitable?
The Type A, it can be suitable. Really go by the manufacturer's recommendations of the EV charger itself. There is a trend now that the circuit protection, the earth fault protection, is being inbuilt into a lot of chargers. We then fall into AS3000 because it's a sub-circuit, it needs to be RCD protected. So you'll have requirements there as far as the sub-circuit goes. The Type A can be okay for a lot of them. Type B is without doubt the best protection. It's 100% so. Unfortunately, it is a more expensive device because of the technology that's in it. I think over time, we're going to see these prices come down as volumes go up. And that's typical of any product. But yeah, the Type B would be the best. Some manufacturers of EV chargers are still recommending Type B. Some of them say a Type A, and that'll depend on their internal protections as well.
Yes, I think we are seeing a number of them have the Type Bs inbuilt into their chargers, and then they require then the Type A to apply with AS3000 at the start.
Which it is, and it actually brings in a secondary issue there, because if you've got a 30 milliamp device protecting another 30 milliamp device, the two devices are going to race. It's like having two circuit breakers of the same current rating. So you're not sure which one is actually going to trip, because they're both built to a particular standard and their tripping characteristics effectively are identical. So yeah, it opens a Pandora's box, really.
Yeah. So the next one from Rowan. So is a Type B RCD not particularly to stop VSD nuisance tripping to the circuit, but given a broader range of protection? If so, what type of safety switch would be best to prevent VSD causing some nuisance tripping on that circuit?
I'll go again if you like, Fred. With VSDs, the front end of the VSD is usually chopping up the sine wave a lot. So you chop it up to make it a DC, and then you chop it again to make it the variable frequency. Because of this rapid switching that's going on, the RCD interprets that as a high frequency. And sometimes that high frequency will be getting beyond the capability of the lower level RCD. So that's why a type B, it goes up to, what did we say, 2 kilohertz, I think it was. And that will give that greater immunity to nuisance tripping. So that's a fundamental reason. You know, in Germany, they've actually introduced a type B plus. So we don't see those here in Australia, but they have that, and that has a capability up to 20 kilohertz. So it might be something that will come in the future, but Germany is the only country that I'm aware of that are using that.
Wonderful.
Yeah.
We have one here from Daniel. Do we need to upgrade to a type A from a type AC when we're extending or increasing load on an existing final sub-circuit?
I'll take this one.
Sure.
Yeah. So, yeah, the thing here is with the current explanation and clarifications we have, if you are adding a circuit, you need to definitely, after the 1st of May, it has to be minimum type A RCD. So if you are replacing a type AC, if by the fact that, for example, if it's a broken or it's a damaged RCD and you're replacing it, it can be replaced with the exact same type AC if it suits the application. So that's the point regarding the replacing the type AC with type AC after the 1st of May. But if it's increasing the current or if you're adding a new circuit, definitely need to be minimum type A.
Sorry, I think I'll just correct on that one there as well. If it's an existing circuit and we're to say adding an extra power point to the circuit, we would not need to change over the RCD type at that point. I believe is the advice that we received from ERAC recently on existing circuits. I don't know if we had to upgrade it because it was existing with a circuit breaker. A couple of questions here, pretty much in that same vein that I'm going to tick off with. There was one question here regarding is the type AC can still be used to replace the type AC? We just covered that one. That was part of the advice MEA sent out at the start of the week with regards to the new ERAC notice in regards to that. So yeah, same again, if you are replacing a type AC that is damaged, you can put another type AC in. This is generally more used in the situations where we have existing chassis style switchboards of which the manufacturer does not have a specific type A available for replacement and refitment back in. But we'd always recommend where possible to upgrade to those type A's. Next question here. Oh, hello, is there any 3-phase 10 milliamp RCD or greater than 32 amp single phase options coming to the market from IPD for use in medical applications?
3-phase 10 milliamp. No, I don't think anything in the pipeline at the moment. Yeah, for the for those ranges that has been questioned. No, nothing at the moment in the pipeline.
Okay.
That I'd love to say it's a work in progress, and I think it potentially could be, but it's a long way down the track.
Sure. With regards to existing stock on hand of type ACs, will suppliers be offering a credit, or where there is a type A allowable, perhaps a replacement? I'm not sure if IPD have any stock that they were trying to handle with handovers. What are you guys doing with that space?
Look, for different channels, we have different policies. So obviously the best advice you can get is if you have definitely a sales rep, contact him. He will tell you the latest advice that we have, because, you know, by the time that we get closer to the deadline, we had some announcements to the market, and also the fact that we gave some deadlines to our customers to return their stock that might not be, it's not going to be any good to them. So every channel has its own, messages. So if you contact your sales rep, you will get the best advice from them.
Definitely agree. Talk to your wholesalers, talk to your sales reps, guys, for those ones.
Yeah,
I think it's very important for any of the guys, if they've got some type ACs rattling around in the back of their van, they've got to be super cautious that they don't just grab an RCBO, for example, and put it into a job, because they have to have that awareness of the type A, type AC situation. And we've all been in that position where we're running around in a car, we've got a bit of stock in the back of the van, and some of it is incredibly old. So just be careful, guys.
Yes, definitely. One here that I think I can answer pretty quickly. Do we need to install RCDs for a solar system? If so, what type of RCD should be used for residential? Primarily, AS3000 does not actually require an RCD to be installed for a solar generation system from an inverter, as it's considered a generation source. But if the manufacturer does specifically say that an RCD shall be installed, we would follow that instruction. And then they would normally specify the type of RCD to go along with it. Next one. Is there a simple and accurate way to measure total leakage current of appliances connected to an RCD protected circuit?
There's a variety of instruments that are capable of checking a leakage current. They've been around for many, many years, and I think the newer ones are obviously getting more accurate. So yes, there's various test equipment that you can get that will check that. Some of the leakages on filtering circuits, and because of the higher frequencies and things, it makes it a little more difficult sometimes. But yeah, there's some of the handheld equipment is actually quite good.
Yeah, I've seen a few of the milliamp clamp meters available, so they're definitely getting more prominent in the market as people are buying them, and the price is finally starting to come down a bit on those too, I think. Okay, so what's an approximate cost of a type A versus a type F or type B RCD?
All right. The approximate difference cost, I can tell you in percentages. First thing you need to consider is, you need to know is, for every range that those types are available, it might be different from another range. Like if you look at, for example, a single pole RCBO, or if you look at a 4-pole RCBO, that they are going to be different costs and different percentages involved. As a rough figure, between type A and type F, it's something between maybe, I can tell you, around, in some cases around 10 to 20%, something like that. So it's not as expensive as expected in some of the ranges. And in some ranges, depends on the size and the number of circuits need to be protected, and all of the bits and pieces come in, it goes up to maybe 2 times between type A and type F.
Wonderful. So we've got another question here. Would an RCBO trip if there was a reverse polarity situation on the mains?
Reverse polarity situation.
Yeah, I'll answer that one. The answer is generally going to be no, especially if that's on the mains, being that you're measuring downstream. If there was to be a transposition though with perhaps neutral and earth, that's when we would see it out in the final sub-circuit, but it's going to have to be downstream of the RCBO.
And just in the fundamentals, all the RCD is looking at is the current through the load going on an active and then returning on a neutral, and it's looking for that balance between the two. Now, whether it senses it through a toroid or electronically or however, it doesn't matter. The fundamental is the same. So as long as that balance is occurring, the RCD shouldn't trip. It's when there is an imbalance, the RCD basically says, well, it's got to be going somewhere. Presumably it's an earth fault, therefore we trip.
Excellent. Question here. New Zealand's been installing Type A's for longer than Australia. Is there a reason for this if the standard is shared?
That's been the question asked many, many times for many, many years. You could say, and we hate to say it when New Zealand's ahead of Australia, but they are slightly more advanced in that. They recognised quite some years ago that electronics was coming into loads, and they made the decision that their minimum requirement was a Type A. In Australia, for whatever reason, it was decided that we would hold back. We've now made that choice, and we're aligning ourselves more with the New Zealand requirements within the standard. And the same can be said about AFDDs that we mentioned before. New Zealand have instilled certain requirements for the installation of AFDDs. So in Australia, we've included AFDDs in a reasonable section of the standard, and there's a good appendix talking about it. You can see that as we go through the generations and the various editions of a standard, we've now introduced the informative sections. It won't be long, I would suggest, until it becomes a normative, and we're going to see AFDDs being a requirement.
Yes.
That'll be for some time in the future.
Definitely. Next question. Are Type B RCDs required by the standard for VSD circuits?
I don't think they're required by the standard, but often they're recommended, and it's more by the manufacturer's recommendation. What you're really looking for is to select a product which is not going to be subject to nuisance tripping. That's the major thing. And you also want to make sure that the product you select is suitable for the load that you have. And we've been through the variety of sizes. VSDs can be quite nasty. Some are really good and some are really awful when it comes to leakages and what they do to the supply, harmonics and all sorts of things. I hate to bring up the harmonics word because someone's going to ask me about harmonics and RCDs. Yeah, that's really the thing. If the manufacturer of whatever piece of equipment is recommending the upstream protection should be a Type B, you should put in a Type B.
Yep. Excellent. Looks like our final question in here for the moment. Can we provide some field situations where a Type A is still and can be applicable? I would think the only one really in this situation is for existing circuits that have that are already installed. They can stay installed. Referring back to that new ERAC document that's available, one that probably falls into a little bit of a gap here is they talk about where an AC type has been installed prior to the 1st of May in a new construction build, but the circuit's not yet energized. It's discussing that as long as it's been installed and certified, you've done your certificates of test, and the equipment's signed off, they can still stay in that instance. And then finally, if it's an existing circuit of which you have to perform a repair, so the RCVO was actually damaged or failed, and you could swap it out for another Type AC on an existing circuit, as long as it's still suitable to the load types that are connected. Is there anything you want to add to that?
No, I think you've covered that, Matt. Fundamentally, the new requirements about Type A and Type AC and so on, it's not a retrospective change. So anything that currently exists doesn't need to change. But once it's been worked on, we've got to follow those guidelines that Matt just went through.
Excellent. Well, we don't have any more questions here. Unless anyone else has something to pop in, I'll thank you both for joining us today and being very informative for our members. I know they really appreciate the time you put into this.
Well, thank you very much. And thank you to the membership, and thank you, Matt.
No problems. We do have one final question. Let's make this the last one from Jason. Just wanted to clear up something you've been told. A theoretical situation in voltage rise between the neutral and a functional earth. Would that trip the mechanism?
It shouldn't, no. the voltage rise between the functional earth and the neutral.
Neutral, yeah.
It shouldn't. An RCD by its nature is doing a comparison of the load currents going out and coming back. It might depend on the severity, because the functional earth is in the so-called electronic RCBOs. If that voltage level, off the top of my head, I don't know the limit of the voltage. If it gets to an extreme, you could start talking about damage to the internals of the unit. So that's really a slightly separate issue. It shouldn't affect the function of the RCD, but it probably depends on the level of the overvoltage that we're talking about.
Sure.
Do you feel in a similar way about that one, Fred?
Yes, but I was thinking about some other scenarios that if that happens, that's by itself is a different kind of fault. That's what I was thinking about, that if you have voltage between your neutral and earth, because that functional earth anyway going to go to your earth bar. So if you have that's a totally a different kind of scenario. Yeah.
If you're getting significant overvoltages on the neutral, I think you've got another issue to investigate.
Yes, definitely. Yep. Look, we might almost wrap that up there. I'm going to give you one final question. Which RCD would you recommend for a soft starter?
If it's a single phase soft starter, or type F for sure. And when you get into the 3-phase units, where you'd almost treat the soft starter like a VSD, so follow the same recommendations.
Excellent, excellent. Okay, well, thank you very much for joining us. I hope everyone really enjoyed the webinar. And as I said before, you'll get an emailed link shortly with a copy of the video. Thank you all for coming along.
Thanks, Matt. Thanks,
Matt.
everyone.
Thanks for attending,
Thanks, Fred.
guys. Thank you. Cheers.